We have built up our understanding of quantum mechanics, quantum states, gates, and entanglement. Now it's time to put all of this to work. How do we actually use quantum computers to solve real problems? This is where quantum algorithms enter the picture. At its core, an algorithm is simply a defined set of instructions or procedures that a computer follows to solve a particular problem. The objective of a quantum algorithm is twofold: execute calculations more efficiently than classical computers, as well as address computations that are practically infeasible for classical computers due to inherent physical limitations. Think about the nitrogen fixation problem we discussed earlier. Simulating the iron molybdenum cofactor would take billions of years on a classical computer. That's not a limitation of our current technology. It's a fundamental physical barrier. Quantum algorithms offer a way around these barriers. Right now, we are operating in what's called the NISQ-era, noisy intermediate scale quantum devices. Let me break down what this means. Noisy means current quantum computers suffer from errors and decoherence. Intermediate scale means we have dozens to hundreds of qubits, not millions. Quantum means despite limitations, they possess computational capabilities that begin to exceed classical computers. This is a critical transition phase. NISQ devices are not perfect, but they are powerful enough to do things classical computers cannot. They represent our first step into the quantum computing age. Given the limitations of NISQ devices, like limited qubits, susceptibility to errors, short coherence times, we cannot yet run the pure algorithms that theorists dreamed about decades ago. Instead, we focus on hybrid algorithms that harness the strengths of both quantum and classical computing paradigms. The pattern is elegant. Let the quantum computer handle the parts is good at: exploring exponentially large state spaces through superposition and entanglement. And let the classical computer handle what it does well: optimization, control logic, data processing. These hybrid algorithms are pivotal for optimizing performance on NISQ devices and working within constraints of limited qubits, managing errors and noise, and scaling towards more advanced utility-scale quantum systems. Today, we will focus on the algorithms that are actually working in the real world right now, which are quadratic unconstrained binary optimization, also known as the QUBO, quantum approximate optimization algorithm, QAOA, variational quantum eigensolver, VQE, as well as the adiabatic quantum computer. These have proven themselves at addressing a myriad of optimization and quantum simulation challenges. You may have heard of Shor's algorithms for factoring large numbers or Grover's algorithm for database search. These are remarkable theoretical achievements that demonstrate quantum advantage, but they were designed assuming full-scale fault-tolerant quantum computers with millions of error-corrected qubits. We are not there yet. So while we will not explore them in depth in this course, know that they represent the future of quantum computing. For now, let's focus on what we can do today. Central to the NISQ era is the quadratic unconstrained binary optimization, QUBO, problem. QUBO problems are NP-hard. Let me explain what this means. NP-hard problems are a class of problems that are particularly challenging to solve in polynomial time on classical computers. As the size of the problem increases, the time required to find an exact solution grows much more rapidly than any polynomial function of the problem size, typically exponentially. For small instances, these problems are manageable, but scale them up and classical computers hit a wall. The universe will end before they find the optimal solution. Here's why QUBO is so important. Numerous classical optimization challenges can be mapped to the QUBO framework. Problems like max cut, which involve partitioning graphs, graph coloring, the traveling salesman problem, job scheduling, portfolio optimization, as well as machine learning training. If we can solve QUBO problems efficiently, we can solve all of these. Let me show you what a QUBO problem actually looks like using the max-cut problem, one of the most famous combinatorial optimization problems. Here's the setup. You have a graph with vertices and edges. Your goal is to partition the vertices into two disjoint sets such that the number of edges connecting vertices in different sets is maximized. Picture cities connected by roads. You want to divide the cities into two regions to maximize the number of roads crossing between regions. Here is a simple example with 5 vertices. The solid lines might represent strong connections and the dashed lines weaker ones. The challenge: how do you partition vertices 1, 2, 3, 4, 5 into two groups to maximize edge cuts? Why does max cut matter anyways? Let me give you a useful analogy. Visualize each vertex as a city and each edge as a road connecting two cities. The max cut problem then becomes optimally segregating these cities into two regions to maximize the number of interconnecting roads. Another interpretation relevant to social networks is: envision a system of interconnected individuals influencing one another. Each individual corresponds to a vertex, while their interactions are represented by edges. This model captures the strength of influence between individuals, represented by the edge weights. For a marketing strategy offering free products to select individuals, the central goal becomes determining the ideal subset of these individuals to optimize revenue. Here's the problem formulation. The weighted max cut problem can be formally defined as follows. For an undirected graph G with VE in a set comprising of n nodes, where V denotes the vertex set, E symbolizes the edge set, and edge weights are given by W of IG for I and G element of E. The cut divides the vertex set V into two subsets labeled 0 and 1 respectively. The objective is to maximize the total weight of edges that cross the cut, edges that connect nodes in different subsets. By assigning xi is equals to 0 and xi is equals to 1 to each node I, the goal is to maximize the global profit function. This formulation captures the essence. We want to count edges where one endpoint has xi is equals to 0 and other has xj equal to 1. Here's how you map this to an Ising model. Now, here's where quantum computing enters the picture. The max cut problem and QUBO problems generally can be mapped to something called the Ising model. The Ising model originally comes from physics. It was developed to understand magnetism, specifically how spins in a magnetic material interact. But it turns out this same mathematical framework is perfect for describing optimization problems. In a quantum system, finding the ground state corresponds to finding the configuration that minimizes the energy function. We replace classical bits 0 or 1 with quantum spins using the Pauli operators to obtain the Ising Hamiltonian. The ground state of this Hamiltonian, the quantum state with minimum energy, encodes the solution to the max cut problem. The Ising model can be tackled using diverse quantum algorithms, including variational quantum eigensolver, quantum approximate optimization algorithm, as well as quantum annealing via devices like D-Wave. Each approach has advantages depending on the problem structure and available hardware. The applications of the Ising model extend far beyond graph theory. Combinatorial optimization problems like the traveling salesman problem, job scheduling on machine, portfolio optimization in finance can all be transposed onto an Ising framework. This is why QUBO is so central. It's a universal language for optimization problems, and quantum computers are naturally suited to exploring the solution space. In the coming sections, we will deep dive into the QAOA, Quantum Approximate Optimization Algorithm, and the VQE, Variational Quantum Eigensolver. All of these algorithms share a common thread. They map problems to Hamiltonians and use quantum mechanics to explore solution spaces that are exponentially large. Understanding this framework is crucial. When you hear about quantum computers solving optimization problems or simulating molecules, this is the underlying mathematical structure making it possible.